Today we're going to start chapter 22. In chapter 22 we're going to talk about our carbonyl or acyl groups bonded to electronegative atoms. So here are the examples of what we're going to talk about. This first one is called an acid chloride because it's derived from a carboxylic acid, but it has a chlorine. The second kind we're going to talk about are called anhydrides. These actually have two carbonyls connected by an oxygen in the middle. So this is an anhydride. The third kind we're going to talk about are carboxylic acids. You're familiar with those. Those are friends. The fourth one is an ester. So those also fall in this category. And our fifth one is an amide. The amides can also have one or two R groups attached to that nitrogen. The difference between these and aldehydes and ketones, the big ingredient is that that other piece attached to the carbonyl carbon is a good leaving group. So our chlorine, our OH, this whole piece here, this piece here, and this piece here are good leaving groups or can be made into good leaving groups. And so these carbonyls do nucleophilic acyl substitution instead of addition. So you will substitute something for those particular leaving groups. Let me dig into these a little bit more. So our anhydrides, if we look at anhydrides, these can be either symmetrical or asymmetrical. So they can have the same R group on both sides or different R groups on both sides. They can also be cyclic. So if you have an oxygen here, right, that's an anhydride that can also exist. If we talk about amides, our amides can either be primary amides or secondary amides or tertiary amides, where you have the nitrogen bonded to three different things, including the carbonyl carbon. So primary, secondary, or tertiary amides, depending on how many groups are bonded to that nitrogen. When we talk about esters, we can either have the normal ester that we're used to, or we can have a cyclic ester. Cyclic esters have a specific name. They're called lactones. You can even have a cyclic amide. Cyclic amides look like this. These are called lactams. So these are all specific kinds of those functional groups that we're talking about. The other one we're going to see in this chapter is slightly different but still fits in. So this is a nitrile. You've seen these in other things. You've seen it as an addition group to a ketone or an aldehyde as a nucleophile. So they're in a slightly different category, but they have the same oxidation state as the carboxylic acid derivatives. So there's going to be some similarities that we're going to talk about. So let's talk about the structure and the bonding of these carboxylic acid derivatives. So the difference between normal carbonyl structures and these structures is the resonance structures. So if we draw our compound like this, all of our compounds have a lone pair on that Z, and they can contribute so that you have a resonance structure that looks like this. The more basic the Z is, the more it donates to the electron pair, and the more resonance structure, the more that this last resonance structure contributes. So if we look at the pKa of the conjugate acids of HZ, so for instance, chloride, its conjugate acid would be HCl, has a really low pKa. This guy here would be the conjugate acid of the anhydride. This would be the conjugate acid of carboxylic acids. It's approximately the same as those of esters and less than that of amides. So the deal is that the chlorides are the most reactive. The acid chloride is the least stable. So our carboxylic acid compound with the chlorine as Z is the least stable. It's the most reactive. Our amide, on the other hand, is the most stable, and so it is the least reactive out of all of these listed here. Nitriles, on the other hand, look like alkynes. They've got that 180-degree angle with one sigma bond and two pi bonds, and so their carbon atom is electrophilic, but they fit somewhere in a different category than these. How are we going to name our compounds? So these compound names are formed from the names of the parent carboxylic acid. So if this is our parent carboxylic acid, whatever we change that OH to is going to change what our functional group is. So if we have acid chlorides, our most reactive carboxylic acid derivatives in this chapter, they look like this. We're going to name the acyl group and add the word chloride. We're going to change the ic acid. So if it was acetic acid, we're going to change it to YL chloride. It'll be acetyl chloride. So this is acetic acid. If we change that to a chlorine, we have acetyl chloride. This is for acyclic acid chlorides. If it's stuck on a ring, for instance, it looks like this, you're going to change the name, or sorry, hold on. Let's just make it a regular cyclohexane. So if it's on a ring, you're going to change the ending carboxylic acid to the ending carbonyl chloride. So this would be cyclohexane carbonyl chloride. Let's talk about naming anhydrides. So if you'll notice, anhydrides have two R groups. They've got this one and this one. So we can have either symmetrical anhydrides, where both R groups are the same, or we can have asymmetrical anhydrides, or mixed anhydrides. If your anhydride is symmetrical, you're going to change the word acid to the word anhydride. So if this is acetic acid, then its counterpart is going to be acetic anhydride. If you have mixed anhydrides, things are different. So mixed anhydrides, you need to name both carboxylic acids. So, and then you're gonna make those names alphabetical and replace the word acid with anhydride. So if we had something like this, this side would be acetic acid. This side would be benzoic acid. So if we alphabetize them, we have acetic, benzoic, anhydride. If we want to name esters, esters also have two groups. They have an alkyl group bonded to this oxygen, so this would be your alkyl group. And then they have an acyl group, which is this guy over here. So to name your ester, you're going to name the alkyl group first as an alkyl, and then name the acyl group by changing ic acid to ate. So first you name the alkyl group, and then second you change whatever the acyl group, ic acid, to ate at the end. So for example, if I were to have you draw methyl benzoate, first you would draw that group in the middle, that's your ester. Methyl is coming off the oxygen, benzene ring coming off here. Methyl benzoate. Let's name amides last. Well, second to last. So with amides, you replace the ic acid, or if it was oic acid, or ilic acid, with the word amide. If it's a secondary or tertiary amide, you have to name the alkyl groups with the letter N in front of them to show that they're coming off of the nitrogen. So, example, if I said draw a structure for NN, that's a comma, dimethyl acetamide, you would know, okay, we still have this acyl group over here. That's from acetic acid, things like that. There's your acyl group. Here's your nitrogen. And because there is dimethyl, and they both have an N in front of them, both of those methyl groups are coming off of the nitrogen. So that's NN dimethyl acetamide. Last thing we're going to name is nitriles. So with nitriles, you just name them as an alkane derivative. These are our C triple bond N things. So name as an alkane derivative. So you just want to find the longest change with the CN, add the word nitrile to the name, and make the CN group number 1. So if we have this, 1, 2, 3, 4, 5. So you have 5, and so this would be pentanitrile. if it's called if it's a substituent on a ring or on a big molecule, it's called the cyano group. The most common one is acetonitrile. Oh, hold on, I missed a carbon. Acetonitrile, that's a common name for one. So what are some of the physical properties of our acid? So what are some of the physical properties of our carboxylic acid derivatives? First of all, they once again have that polar carbonyl group. That's going to make them react as electrophiles again. Primary and secondary amides can do hydrogen bonds. Because they have a hydrogen coming off of a nitrogen. So that means that the primary and secondary amides have higher boiling points and melting points than comparable alkanes. Because they can do that hydrogen bonding. The rest have similar melting points and boiling points to regular alkanes. All carboxylic acid derivatives are soluble in organic solvents. And because of their polarity, most that have less than 5 carbons can dissolve in water. Because of the hydrogen bonds of water and that polarizing force there. And that's the end of our lecture for today.